Welcome to Chapter 12 of Class 10 Science, Magnetic Effects of Electric Current. In this fascinating chapter, we'll explore one of the most important connections in physics, the relationship between electricity and magnetism. In the previous chapter, we studied the heating effects of electric current. But did you know that electric current can also produce magnetic effects? This fascinating connection between electricity and magnetism forms the basis of many modern technologies. From electric motors that power our appliances to generators that produce electricity, electromagnetic principles are everywhere around us. We'll explore how electric current creates magnetic fields, how to determine the direction of these fields, and how magnetic fields exert forces on current-carrying conductors. We'll also study electromagnets and their applications in various devices. This chapter builds on our understanding of both electricity and magnetism to explain how they work together to create the technologies we use every day. Let's begin with understanding magnetic fields and field lines. We know that a compass needle gets deflected when brought near a bar magnet. A compass needle is essentially a small bar magnet with north and south poles. The region surrounding a magnet, where its influence can be detected, is called a magnetic field. Magnetic field lines are used to represent magnetic fields visually. These are imaginary lines along which a hypothetical free north pole would move if placed in the field. Magnetic field lines have several important properties. They emerge from the North Pole and merge at the South Pole. They form continuous closed curves. The tangent at any point gives the direction of the magnetic field. They never intersect each other. Closer lines indicate stronger magnetic field, and inside the magnet, field lines go from south to North Pole. The relative strength of the magnetic field is shown by how close together the field lines are. We can visualize magnetic fields using iron filings, which align themselves along the field lines when sprinkled around a magnet. Now let's explore Oersted's groundbreaking discovery. Hans Christian Oersted discovered in 1820 that an electric current creates a magnetic field around it. In his experiment, he noticed that a compass needle deflected when current flowed through a nearby wire. This was a revolutionary discovery because it showed for the first time that electricity and magnetism were related phenomena, not separate forces as previously thought. We can demonstrate this with a simple activity. When we place a straight copper wire perpendicular to the plane of paper with a compass nearby, we observe that when current flows, the compass needle deflects. When current stops, the needle returns to its original position. Reversing the current reverses the deflection direction. This shows that electric current produces a magnetic field around the conductor, and the direction of the field depends on the direction of current. This connection between electricity and magnetism is called electromagnetism. Let's examine the magnetic field pattern around a straight current-carrying conductor. When electric current flows through a straight conductor, it produces a magnetic field consisting of concentric circles around the wire. The planes of these circles are perpendicular to the wire. The strength of the magnetic field increases with increasing current and decreases with distance from the wire. It is the same at all points equidistant from the wire. We can demonstrate this with an activity using a thick copper wire passing through cardboard and connected to a battery. When we sprinkle iron filings, they form concentric circles around the wire. The field strength increases with current and decreases with distance. The direction reverses with current reversal. The pattern shows concentric circles with the wire at the center. The magnetic field strength is directly proportional to the current. Double the current means double the magnetic field strength. It's inversely proportional to the distance from the wire. Double the distance means the magnetic field strength halves. The complete relationship is B proportional to I divided by R. Now let's learn about the right-hand thumb rule, which helps us determine the direction of the magnetic field around a current-carrying straight conductor. This rule, also called Maxwell's corkscrew rule, provides a simple way to visualize the relationship between current direction and the resulting magnetic field direction. According to the right-hand thumb rule, imagine holding the current-carrying straight conductor in your right hand such that the thumb points in the direction of current. Then the curled fingers will point in the direction of the magnetic field lines, which are concentric circles. Alternatively, according to Maxwell's corkscrew rule, if a right-handed corkscrew is driven in the direction of current, then the direction of rotation of the corkscrew gives the direction of magnetic field lines. These rules are very useful for solving problems involving magnetic field directions around straight conductors. Now let's explore the magnetic field due to a circular current loop. When a straight current-carrying conductor is bent into a circular loop, the magnetic field pattern changes significantly. At the center of the loop, the magnetic field lines are straight and parallel. The field is strongest at the center and decreases as we move away from the center. The field lines are concentric circles near the wire, but at the center, they become straight and parallel. All sections of the circular loop contribute to the field in the same direction at the center. The field strength is proportional to the current and the number of turns. For a coil with N turns, the magnetic field is proportional to N times I. We can demonstrate this with an activity using a circular coil with many turns through cardboard connected to a battery. The iron filings show the magnetic field pattern with field lines crowded near the wire and straight parallel lines at the center. The pattern is similar to that of a bar magnet, showing that a current-carrying circular loop behaves like a magnetic dipole. Let's now study solenoids and their magnetic properties. A solenoid is a coil of many circular turns of insulated copper wire wrapped closely in the shape of a cylinder. It's essentially a long helical coil. When current flows through a solenoid, it produces a magnetic field very similar to that of a bar magnet. One end behaves as a north pole and the other as a south pole. The magnetic field lines are parallel straight lines inside the solenoid, making the magnetic field uniform inside. The field is strong and concentrated inside but weak and diverging outside. The field strength is proportional to the number of turns multiplied by the current. The uniform field inside makes solenoids very useful. When a soft iron core is placed inside a current-carrying solenoid, it becomes strongly magnetized. This arrangement is called an electromagnet. Electromagnets have several advantages. Their magnetic strength can be controlled by current, they can be switched on and off, very strong magnets can be made, and their poles can be reversed by reversing current direction. Electromagnets are used in electric bells, relays, motors, and many other devices. Now let's explore the force on current-carrying conductors in magnetic fields. French scientist André-Marie Ampère suggested that if a current-carrying conductor produces a magnetic field that exerts force on a magnet, then the magnet should also exert an equal and opposite force on the current-carrying conductor. This mutual interaction between magnetic fields and current-carrying conductors is fundamental to the operation of electric motors and many other devices. We can demonstrate this force with an activity using an aluminium rod suspended between the poles of a horseshoe magnet and connected to a battery. When current flows, the rod gets displaced. The displacement direction reverses with current reversal and also reverses with magnetic field reversal. Maximum displacement occurs when the current is perpendicular to the magnetic field. This shows that a current-carrying conductor experiences force in a magnetic field. The force depends on the current, magnetic field strength, length of conductor in the field, and the angle between current and magnetic field directions. Now let's learn about Fleming's left-hand rule for determining the direction of force on a current-carrying conductor in a magnetic field. English physicist John Ambrose Fleming gave this simple rule, which is extremely useful for understanding the working of electric motors and many other electromagnetic devices. According to Fleming's left-hand rule, stretch the thumb, forefinger, and middle finger of your left hand such that they are mutually perpendicular to each other. The forefinger points in the direction of magnetic field, from north to south, the middle finger points in the direction of current, and the thumb gives the direction of force or motion. Remember, use your left hand for motor effect, where force produces motion. This rule helps us determine which way a current-carrying conductor will move when placed in a magnetic field, which is crucial for understanding how electric motors work. Now let's study electric motors, which convert electrical energy into mechanical energy. Electric motors work on the principle that a current-carrying conductor placed in a magnetic field experiences a force. Electric motors are used in numerous applications, from small toys to large industrial machines, from electric fans to electric trains. The main components of an electric motor are the armature, which is a rectangular coil of many turns of insulated copper wire, a strong field magnet that provides the magnetic field, a split ring commutator that reverses current direction, brushes that conduct current to the commutator, and an axle, which is the rotating shaft. The split ring commutator is crucial for continuous rotation. The working principle involves current flowing through the armature coil, which experiences torque in the magnetic field, causing the coil to rotate. At the vertical position, the commutator reverses the current, which maintains rotation in the same direction. This process repeats for continuous rotation. Fleming's left-hand rule determines the rotation direction. Now let's explore electromagnetic induction, discovered by Michael Faraday. In 1831, Faraday discovered that electricity could be produced from magnetism, the reverse of Oersted's discovery. This phenomenon is called electromagnetic induction. Faraday found that when a magnet is moved relative to a coil, an electric current is induced in the coil. This discovery laid the foundation for electric generators and transformers. We can demonstrate this with an activity using a coil connected to a galvanometer and a bar magnet. The galvanometer deflects when the magnet moves relative to the coil. The deflection direction reverses with motion direction reversal. Faster motion produces larger deflection, and no deflection occurs when the magnet is stationary. A stronger magnet produces larger deflection. This shows that relative motion between a magnet and a coil induces current. The magnitude of induced current depends on the speed of relative motion, strength of magnetic field, number of turns in the coil, and the area of the coil. The direction of induced current depends on the direction of relative motion. Now let's learn about Fleming's right-hand rule for determining the direction of induced current. Fleming also gave this rule to determine the direction of induced current in a conductor moving in a magnetic field. This is particularly useful for understanding the working of electric generators. According to Fleming's right-hand rule, stretch the thumb, forefinger, and middle finger of your right hand such that they are mutually perpendicular to each other. The forefinger points in the direction of magnetic field, from north to south, the thumb points in the direction of motion of the conductor, and the middle finger gives the direction of induced current. Remember, use your right hand for generator effect, where motion produces current. This rule helps us determine the direction of current induced in a conductor when it moves through a magnetic field, which is fundamental to understanding how generators work. Now let's study electric generators, which convert mechanical energy into electrical energy. Electric generators work on the principle of electromagnetic induction discovered by Michael Faraday. Generators produce the electricity that powers our homes, industries, and cities. They are essentially the reverse of electric motors. The main components of an AC generator are the armature, which is a rectangular coil of many turns of insulated copper wire, a strong field magnet that provides the magnetic field, slip rings that conduct current to the external circuit, brushes which are stationary graphite contacts, and an axle which is the rotating shaft. Note that generators use slip rings, while motors use split ring commutators. The working principle involves the armature coil rotating in the magnetic field, which causes the magnetic flux through the coil to change continuously. This changing flux induces alternating current. Current flows through the slip rings and brushes, and its direction reverses every half rotation, producing alternating current. In India, the AC frequency is 50 Hz, meaning 50 cycles per second. Now let's understand domestic electric circuits. Electricity reaches our homes through a complex system of power stations, transformers, and transmission lines. The domestic circuit distributes this electricity to various appliances in our homes. Understanding domestic circuits is important for both safety and efficient use of electricity. The main components of a domestic circuit are the electric meter that measures energy consumption, the main switch that controls the entire house supply, the fuse or MCB, which are safety devices against overload, the live wire that carries current at high potential, the neutral wire that completes the circuit at zero potential, the earth wire which is a safety connection to ground, and the distribution board that distributes electricity to different circuits. In India, the voltage is 220 volts and frequency is 50 Hz. All appliances are connected in parallel because this provides the same voltage across all appliances, allows independent operation, ensures that if one appliance fails others continue working, and allows each appliance to get the required current. Series connection is not used as failure of one appliance would stop all others. Finally, let's discuss electrical safety measures. Electricity, while extremely useful, can be dangerous if not handled properly. Electric shocks can cause serious injuries or even death. Therefore, various safety measures are incorporated in domestic circuits. Understanding these safety features helps prevent accidents and ensures safe use of electricity. The main safety devices are electric fuses, which are thin wires of low melting point material connected in series with the live wire that melt when current exceeds safe limit, breaking the circuit to prevent damage. Miniature circuit breakers or MCBs, which are automatic switches that trip during overload and can be reset after the fault is removed, making them more convenient than fuses, and earth wires, which provide a safe path for leakage current. Earthing or grounding provides a safe path for leakage current to flow into the ground. It prevents electric shocks when touching metal body of appliances, damage to appliances due to voltage fluctuations, and fire hazards due to short circuits. The earth wire is connected to a metal plate buried deep in moist earth.